So good evening everyone. Today we will be discussing about this electron microscopy. In our last class we have been discussing about this optical microscopy, right? Now the difference between the optical microscopy and the electron microscopy, as the name itself suggests, is that in optical microscopy we have seen that we are using visible light, whereas in electron microscopy we will be using a beam of electrons. Okay. Again, in the optical microscopy we have seen the architecture of the microscope is something like this. We have a source, then we have a condenser which helps in the condensation of the light. So this condenser, what it does is that it gathers the light from the source and then it focuses it onto the sample platform. So basically we will be having the sample. Okay, so we have the sample, then after the sample we were having objective lens. It was collecting the light from the samples, diffracted light from the samples, and then we were having the optical tube, and after that we were having either the eyepiece, objective lens oval, and then we were having the eyepiece, or we could have the detector. Detector means the camera. Okay. Now, herein, when we talk about this electron microscopy, we would be having a similar architecture. However, as I told you, the source over here, it would be an electron source. So the source of electron which generates electrons, it is regarded as electron gun. So instead of the light, visible light, we will be having electron gun. Then we have the condenser. Here also we will be having the condenser. However, this condenser, it is regarded as electromagnetic condenser. Okay, electrons, they are charged particles and they will be having electrical charge with it, and when it moves, so to regulate that movement of the electrons, we need to have an electromagnetic field, and the condenser, in the case of electron microscopy, it would be an electron, this electromagnetic condenser. Okay, then the light, it will interact with the sample. Here also you will be having a sample stage. In this case also we are having the sample stage. Here also we will be having a sample stage. Then we will be having a set of objective lenses or lenses. So in this case again the lenses, they are electromagnetic lenses. Okay, we will be having electromagnetic lenses. Then we will be having a detector. So the detector is usually a CMOS camera over here also, because or you can have any other semiconductor array systems also, which are capable of collecting the electrons and recording the intensity levels. Okay. Now this microscopy, in our case we called it upright microscopy or inverted light microscopy. So basically how the light is interacting with the sample, the light is getting transmitted. So in other words, we can say that this is an transmission optical microscope. Okay. However, the similar arrangement In the case of electron microscopy, it is regarded as TEM. So TEM, it is basically transmission electron microscope. Okay. So as the name suggests, the electron beam, it will be transmitting through the sample in the case of transmission electron microscope. In the second case, we have studied another type of microscopy, right? In that type of microscopy, what we have seen? We have seen that we will be having a source, okay? Then there will be condenser, okay? Then there will be a sample, okay? The light from this condenser, what it will do? It will strike on the sample and then it will be reflected back, okay? And while it is reflected back, it will be captured by an optical lens, or we can say objective lenses, which will magnify the optical signal, and then what we will do is that we will be recording the signal through a camera or a detector. Okay, so this was regarded as reflected light microscopy. Okay, there is another type of electron microscopy which is similar to this reflected light microscopy, and it is called scanning electron microscopy. Scanning electron microscopy. In short, it is called SEM. So when we talk about electron microscopy, basically the electron microscopes, they can be categorized either as transmission electron microscopy or scanning electron microscopy. The optics, not the optics, the focusing elements on the lenses which are used to control the electron beam in the TEM and the SEM, they remain the same. Okay, they are similar. Right. Another important thing, when we generate this electron beam, its energy is higher. It is having a high energy as compared to the optical beam, and correspondingly the wavelength of the electron beam, it would be much smaller. And since it is having a much smaller wavelength, so what will happen to the resolving power of the microscope? We have discussed in the case of optical microscope, D, which is basically the distance between the 2 point objects which can be resolved with the microscope, it was given by D is equal to 0.61 lambda divided by numerical aperture of the system. So we can say D was directly proportional to the lambda, and we discussed that the resolving power RP of the camera, it was inversely proportional to the lambda. Now what is happening over here? When you talk about the electron microscopy, what is happening over here? The wavelength is lower than the optical wavelengths, right? So optical wavelengths, what is the wavelength range? It is in the wavelength range of 400 nanometer to 800 nanometer, right? So herein we will be having wavelengths much lesser than the optical wavelengths, and hence the resolving power of the electron microscope, they would be higher. Okay, it would be higher over here. Now why it is higher? Can anyone tell me why it is higher? Why the resolving power of the electron microscopes, it would be higher than the optical microscope. Yeah, but anything else? Lambda I have already told you. Anything else? For understanding this, we need to go to the this high school science, where we discussed, suppose there is an opening, there is a slit, okay, and the slit is quite high, quite large. High means it is quite large. So we have a light source, and then we have a 2D detector plane which will be imaging the light which is coming out of this optical source. So what will happen when the slit is very high? All the rays from this light, it will be passing through the slit, and we will be having the image of the source on the detector, right? Now, consequently, if we reduce this size over here, then what will happen? Then we will find there would be some rays which are gaining entry. We will not get the full picture of the source. However, we will see that there is an increase in the diffraction across the slits, right? Across the what you call edge of the slits, right? Now, herein we will be able to image a portion of the source, but there will be an increased diffraction of the light, and due to that increased diffraction of the light, what will happen? The image what we were getting, the quality of the image, it will be degrading. Okay. Now, if we further reduce this size, we will get to a point where most of the lights, they are getting diffracted, and we will not be having any information about the source onto the screen. Okay. Now, there is a relation between the diffraction and the wavelength. Higher the wavelength, higher is the diffraction. Okay, higher the wavelength, higher is the diffraction. Okay. Now, due to this reason, what happens? The violet, which is just near to the UV region, it is having the, in the visible spectrum, I am talking about in the visible spectrum. In the visible spectrum, it is having the lowest wavelength, and as we go towards the higher wavelengths, we reach the red light, and after that we get to the infrared zone. Okay. Now, if we get to the R within the visible spectrum, it would be having the highest wavelength, and you will find that in the case of red light, the diffraction would be much higher. Okay. So, suppose I give you an hypothetical situation that you are given a chance to image one object which is very small. Okay. And you are given an option that you can choose your specific wavelength of light. So which one you will study, which one you will use, basically which wavelength you will be using. So you need to see what is the magnitude of the size of the object. Okay. So what happens usually, suppose you are having a wavelength of say 600 nanometer, then it will be able to interact with an object of approximately 1200 nanometer in a proper way. Okay. Why that is so? Because in that 1200 nanometer you will be having this wavelength which is getting interacting with this 1200 nanometer particle in a proper manner. Okay. However, if you go towards this 900 nanometer, the interaction would become less. Okay, and when there is a lesser interaction, the information what you are getting from the rays which are coming out after the interaction, you will be getting lower information. Okay, so in this way you will be able to understand and you will be able to find out which wavelength of light you may use to understand the morphology of a particular object. Okay, so analysis of the objects of any particular object, it depends on the analysis, it depends on the nature of the interaction of that electromagnetic radiation with the object. Hence, you will find that in the case of optical microscopy, we do not use the optical microscopy to analyze submicron particle. We do not use it to analyze submicron particles. Now, if we need to go towards the submicron particles, we need to go towards scanning electron microscope, which is having slightly higher energy as compared to the optical wavelengths, right? And it will give you information about the micron size particles. Okay, so 600 nanometer particle or 700 nanometer particle, you will get sufficient information from there. However, if you want to analyze nanostructures, in that case you need much higher energy, and that much higher energy, it can be provided in the transmission electron microscopy. It may be obtained from the transmission electron microscopy. Okay. Now this transmission electron microscopy in transmission electron microscopy, you will be having electron beams which are coming out at a much higher energy. Okay, and in that case, that is the reason that it allows you to get information about the nanostructures. Okay, so if it is in the somewhat in the micron size, in the upper micron sizes, you can use optical microscopy. If you want to get into the micron size range, you can get into this 700 nanometer or 800 nanometer scale. You can use scanning electron microscopy. However, if you come below this around 100 nanometer size range, then it is better that you work with transmission electron microscopy. Okay. Now, as I told you, an electron microscope, it uses a beam of accelerated electrons as a source of illumination. Okay. The wavelength of electron can be up to 1 lakh times shorter than that of the visible light photons, and since it is having a lower wavelength, it is having a higher resolving power than the light microscopes, and that is how you get the much better information. Another important thing, in optical microscopy, we get the images in the color format. Okay, if you put a dye and if you look into the image, you will see if the dye is red colored, then you will find that the image is also having a red color. If the dye is having a yellow color, you will see that the image is again having a yellow color. So what happens in the electron microscope? Any idea? What happens in the electron microscope? So what type of image you will be getting? Will it be a color image? No. Why? Yeah, electrons are charged particles and they do not have any color information over there. Color information is associated only with the optical region. Okay, and even the detectors, when we talk about the color camera, How does a color camera work? Any idea? Because the sensor for detecting the electron beam and a photon, both are CMOS cameras or any other semiconductor devices or the CCD camera. So what makes a color camera a color camera? In color cameras, we have R, G and B color filters. Okay, and these filters are so small, they are arranged in a particular way, and then they are average. I am not going into the construction of that. So what happens over there, you collect the light or the photons which are passing through the red filter, green filter and blue filter, and then using the software you do some manipulation and then you synthesize the color in the software. The sensor does not detect the color. The color is being detected or it is being synthesized after the signal has been captured by the camera in the software. Okay. Pardon? Color is? Yeah. Very good question. Anyone who can answer to this? Color is, he is saying that color is related to the frequency, or we can say it is related to the wavelength. So if you change the electron frequency, we should get the color information. So why this is so? We do not get the information. Few moments back only I told you the color information is being displayed only in the region of 400 nanometer to 800 nanometer. So you work only in this region. Okay, so in this region only, if you are having this frequency, electromagnetic radiation is having frequency in this region, then only you will be getting the color information. If you go outside this region, whether you go towards the UV region and the other electromagnetic radiations, or if you go higher than this infrared light, you will not get any information. Even if you see, there are many cameras which are regarded as no IR filter camera. So in no IR filter camera, what happens? In that case, usually in color camera, an IR filter, IR cutoff is being put up, so that what are IR radiation are longer radiations and they lead to the heating up of the sensor. So in those cases, in the color cameras, we put an IR filter so that the IR filter, it filters out the IR wavelength. Okay, and the sensor is not unnecessarily heated. Okay, in no IR camera, you will find that there is no IR here, and if you try in many of this modern day cameras, you will find that there is no IR camera, because you will find it is having a 3 cameras or quad cameras are there, right? So at least one of the cameras they give as the with a no IR filter. So if you put an IR source, it will be invisible to you, but if you put it and put on your camera, you will find that you are getting the image. That is the reason why you are getting the image. So there are certain cameras which are not having IR filters in front of them. Okay, now I hope it is clear. So the electron microscope image, they will not be having any color information. Okay, so a scanning transmission electron microscope, it can have a better resolution as compared to the 50 picometer. Okay, that means if there are 2 particles which are 50 picometer apart, the transmission electron microscope, it will be able to pick up that magnification. Okay, and herein we can get magnifications up to this 100 lakhs, or we can say 10 millions. Okay, whereas the light microscopes are limited by diffraction, as I already told you, to about 200 nanometer resolution, and they are useful at magnifications below 200x. Okay, in certain things, you will find people are claiming that they will give you 2500 magnification optical zoom. Don't go for that, because practically it is not feasible, because the diffraction of the light, it would be so high that you will not be able to achieve that high what you call the high magnification. Okay. And as I already told you, in electron microscope, this electron optical lens systems, in short it is also regarded as electromagnetic lenses, they are used to shape up the electron beam, and they are analog to the glass lenses which are present in the optical light microscope. This I have already told you. For a resolution of an optical system, we usually get 200 to 215 nanometer of resolution. That means if there are two particles which are 200 to 250 nanometer apart, you will be able to distinguish those particles. Now this image on the left, it gives you an information about how the electron beam interacts with a matter. So apart from all the other things, what we are interested in is that we are interested in three interactions. The first one, secondary electrons are being released. Second, scattered electrons are there, they are being generated. And third is that characteristics X-rays are being generated over here. Okay, and these three, 1 to 3, they are being very useful in the case of scanning electron microscopy. Okay, because it is working in the reflected mode. It is working in the reflected mode. Okay. So these secondary electrons and the backscattered electrons, they are directly working, or they are used for imaging the sample. Okay, so secondary electrons and the backscattered electrons, they are used in scanning electron microscopy for imaging purpose. Whereas this third one, the characteristics X-rays which are being generated, these X-rays are called energy dispersive X-ray. Energy dispersive X-ray. Okay. Now, what is happening over here? So in the case of this secondary electron generation, this electron beam, the electron comes and it knocks out an electron from the atomic structure to generate secondary electrons. Okay, so these electrons, they are being captured. Okay, in the second case, we have this electron, then it goes, interacts with the sample, and it takes a U-turn. Okay, and this type of electrons, they are regarded as backscattered electrons. Okay, the identification of both secondary electrons and the backscattered electrons, they are being done by the same electrodes, same detector, not electrode, same detector. Okay, so we have electron detectors. Okay, so capturing of the secondary electron and the backscattered electrons, they are being done by the same detector. So how the detector finds out that the electron, it is a secondary electron or it is a backscattered electron? Anyone? Based on energy, how? Which one will be having high energy? No, it is the other way around. See, herein your PE, it is coming, it is interacting, it is knocking out this electron from here. So majority of the energy would be needed over here to knock it out from the orbital system. Okay, so the energy with which these secondary electrons will be generated, it will be lower, right? So as is said, the detection of the secondary electrons and the backscattered electrons, it is being done using this energy regulated filter. Okay, so if it is higher the energy, then the detector records it as a backscattered electron, and if it is a secondary electron, it would be having a lower energy. And lastly, we will be having some characteristics X-rays, and these are being formed when the electrons are being moved from the inner orbitals. Okay, and in that case, the electrons from the higher orbitals, they would be coming in, and while they are coming in, they are losing energy. And how do they lose energy? They lose energy by releasing X-rays, and these X-ray beams, what are being generated, they are characteristics for a particular atom. Okay, so in a scanning electron microscopy, you will be getting both the image and the X-ray information, and this X-ray information, it can give you indication how many phases are there, if there are more than one atom, more than one phases are present, because when we talk about the phases will be having different kind of atomic arrangement, and those atoms, as I told you, each atom, they will be having their own characteristic wavelengths. Okay, own characteristics, these X-rays, X-ray wavelengths will be there, and from there we can do the analysis. And this kind of analysis, it is called EDX analysis or EDX analysis in scanning electron microscopy. Okay. Now coming to the how the electrons are being generated. So we have a filament. Now this filament, it is usually made up of tungsten. Okay, this filament, you must have seen this tungsten filament in the normal bulbs. You must have seen this transparent bulbs. I don't know, because many of the bulbs has been replaced with the LED bulbs nowadays. So but still these tungsten bulbs, they are available, and they are quite cheaper. And if you see, there is a coil within that bulb. That coil, what we see, it is a tungsten filament. Okay, now in the electron gun also, we are having a tungsten filament, and it is being heated at a very low voltage, approximately 6 to 12 volt. This thing, it is used to energize the tungsten filament, and when it is being heated with that small voltage, so what happens is that the electrons, they are generated, but these electrons, they do not have sufficient energy to come out of the filament. Okay, now to create this electron beam, what it is done is that we use an anode. Okay, so we use an anode. Anode will be having, they are positively charged, right? Since they are positively charged, we are already having electrons which are around. They will be attracted, or in other words, you can say they are being accelerated towards the anode. Okay, now when they are being accelerating towards the anode, they may go in a wavered manner. The acceleration may be in this direction, so it may be in a different direction. Okay, but we need to channelize this electron beam. So what it is done, this Wavelength cylinder, it is used, it is basically, it is having a cathode. So now what the electrode is sensing, it is sensing that there is a high accelerating force. However, at the same time, there is a local field due to this cathode. Okay, so what this cathode does over here is that it creates a local field like this, and it creates an electromagnetic gate. Now the electrons, they are only able to come out of this cylinder through this open region. If you increase the field of the this electromagnetic gate, at some time it may so happen that there would be no space for the electrons to come through that electric field. Okay, so under that condition, your electron movement through this gate, it will be totally stopped. Okay, so if you want to have a high electron density which is coming out, then you need to keep a low field in the EM gate, and if you want to lower the energy, or if you want to lower the density of the electron beam, then you slowly start to increase the field of the cathode, this wavelength cathode. Okay. Now usually in a particular this electron gun, the temperature, it may rise up to 2700 degrees centigrade, and this voltage between this anode and the tungsten filament, it is having a voltage of approximately 200 to 300 kilovolt, and the wavelength which is being generated, it is approximately 2.5 picometer, and this gives us a resolution of nearly 0.1 nanometer. Okay, now this is a what do you call the architecture of a hairpin style tungsten filament. Okay, and there is another type of filament which is given by LaB6 filament, and this has this can also be used for the electron generation. Okay, so this is a transmission electron microscope. Now you must have understood by this time what should be there. We are having a high voltage for the electron gun, so this is a high voltage cable. Then we have a condensing lens, then we have a condenser aperture. So in the condenser, we have seen that in the optical system, so we have talked that the condenser, it can accept the light, but how much light we will be getting, that can be regulated by an aperture or a diaphragm. Okay, so here also we can have a condenser aperture which will help us in manipulating how much amount of electron beams will be passing through this condenser system. Then we have another second condenser lens. In optical microscopy, we had only one condenser. However, in the transmission electron microscopy, we have two condensers, and these condensers, they are electromagnetic systems or electromagnetic condensers. Okay, then we have this specimen holder and the air lock. Okay, now this specimen holder and the air lock, it is basically a separate system which is totally different from this electron gun. The reason being, the electron gun, it should always have a high vacuum. Why? The reason being, if you are having gas particles within this system, there can be two phenomena. The first phenomena, it may be, in the presence of the gas, it would increase the chances of arc formation, and there will be some sparks which will be generated. And the second thing is that even though sparks are not being generated, you will be ionizing the gas molecules over there. Okay, and when there is an ionization process, the speed of the electron beam, it will come down, and we do not want that to happen. And because of this reason, these electron guns, they are very high vacuum systems. Okay. Then in this specimen holder and the airlock, it is a separate system. So when you take out the specimen, because there is a stage over here, this stage it is being taken out. When this is being taken out, the electron gun system is automatically shut to maintain the vacuum. And again, when you insert this specimen over there, slowly it creates the vacuum over there. And once the vacuum, required vacuum is achieved, then this lock in the electron gun, it is being removed. Okay. Then you have this this sample stage, and from there you have these objective lenses and the aperture, which focuses the electron beam onto the fluorescent screen and the camera for the recording purposes of the image. Okay. So this is a typical transmission electron microscope. Now, how the contrast is being generated? If you see over here, if you have a thick section, it will be darker. If you are having a thin section, it would be lighter. And if you are having a medium thickness, it would be having intensity in between. The scattering and the nature of this thing. When we are talking about how the electrons they are interacting with the system, if you see, if there is a heavy atom, in those cases your backscattered electrons, it will be higher. Okay, and due to that reason there will be very small number of electrons which will be gaining what you call entry, or they will be reaching the detector, and hence it would be darker. So higher atomic systems, they would be appearing darker compared to the lighter atoms. Okay. Then there is an immuno electron microscopy. Over here, what happens is that we have a plastic section, and within this plastic section, antigens are being immobilized. However, it has got some disadvantages. What is the disadvantage? First of all, some of the antigens, they may be interact within the plastic section, and due to this reason, what would happen? These antigens, they will not be available for the antigen antibody reaction. Okay. Second thing, there may be non-specific binding of the primary antibody over the plastics. That can happen. Then what happens? Your primary antibody, it is there. Okay. Now there might be some non-specific binding with the antigen. Okay, that may happen. And then when you use a secondary antibody which is tagged with the gold nanoparticle, what is happening? The distance between the antigen and this gold, it is quite far apart. And due to this reason, if you see, since many of the antigens, they are within the plastic matrix, what is happening? You are not able to quantify the number of the antibodies, because you don't know how many antigens they will be within the plastic matrix or not, right? Secondly, you will not be able to highlight at what specific points these antigens are present, because there is a specific distance between the antigen and the gold nanoparticle which are being used for the detection over here. Because in TEM you need slightly higher molecular weight structures so that you can visualize them. If they are having lower this thing, then they might, because as I told you that there is a very high energy electron beam which is being used, there might be they might burn out. Okay, so we have to be very careful while doing the TEM microscopy, not only TEM microscopy, even the SEM microscopy of the biological materials. Okay. Then this is the TEM image of a cluster of poliovirus. They look something like this. Over here, as I told you, we use a CMOS detector, and these detectors which are used, they are regarded as direct electron detectors. Okay, and these detectors, they are being manufactured by Catan, FEI, and Direct Electron. Okay, then about the vacuum system, they have the vacuum system in the order of 10⁻⁻⁴ Pascal. Okay. Then, as I told you, there might be a generation of the arc if there is no proper vacuum system over there, or there would be a collision of the electrons. Okay. Then in the specimen stage, it includes air logs to allow insertion of the specimen holder into the vacuum. Okay. Another important thing, we have standard TEM grids, because for each analysis we need sample holders. So in the case of TEM, we have TEM grids. So they will be having copper grids like this, CO grids or carbon grids would be there. Then you make a very dilute suspension of your nanoparticles. You put it over the grids and you keep it for drying. And once you keep it for drying, what happens is that you will be getting the nanoparticles which are dispersed onto the grid, and then you take that grid for the TEM analysis. Now in TEM you can also go for the diffraction analysis. Diffraction analysis. Okay, we talked about XRD. In XRD we talked about diffraction. Here we go for electron diffraction. So what is how it is done? It is done by using an objective aperture. If you see, when you are doing the imaging, this objective aperture, it is far apart from the this focal point. Okay, where the electron beams they are getting focused. However, when you go for the diffraction mode, this objective aperture, it is placed at the focal plane, and when you place it, you get this diffraction patterns from there. Okay. Now coming to the same similar architectures. So you have this electron gun, the electron beam is generated. Then you have the first condenser lens. Then you have the spray aperture. It is nothing but an aperture. Then you have the second condenser lens. Then you have the deflection coils. Then you have the final lens aperture, and then you have backscattered electron detector. So basically, this backscattered electrons, it collects both the backscattered electrons and the secondary electrons. Okay. And in some cases, it may be present nearer to the sample at a far off places. Okay, for this secondary electron detector. Okay. Now, apart from that, as I also told you, there are X-ray detectors to detect the X-rays. Okay. Now, what is the role of this deflection point? Suppose you are having a sample like this. Now, when you are looking into this object, you need to analyze a particular section. Your total sample size is this one. Now you need to analyze these things. Okay, this small area within this object. Now, will it do it at a time? No, it is not possible, because in this case you need to make the electron beam incident at a particular point. Then you again move to the right, you take the reading, and in this way you will be first scanning the first line, then you will be coming bit downwards, you will be scanning the second line, then you will be scanning a third line, and you will be having an array of pixels. Okay, the first array is taken within the field of view, then the second array of pixels within the image, it is being captured, then you take that image, then you take the third one, and in that way you scan this area of your interest, so that you get a total image of your field of view. Okay, so in this way we go for this. Another important thing is that for the same analysis we need to coat the sample with a conducting material, usually gold or platinum it is used. Even among the gold and the platinum, either gold or gold palladium alloy, it is written over here, gold or gold palladium alloy, they are commonly used. However, if you want to get a very good quality picture, you can also use the platinum. However, the cost of the platinum, it is very high. Okay, so this is the image of your backscattered backscattered electron. So over here, since the energy is high, if you see, the information content over here is also higher, okay, as compared to the secondary electron. If you see, it is not giving you that much information, okay. Now why it is so? As I told you, higher the energy, higher will be the interaction, and since higher is the interaction, you will be getting more information within the image, okay. Now in this slide, I have given you some information which compares the SEM and the TEM. In the depth of resolution, I have already told you, if there is a thickness, so if you consider this top, so how much information you will be getting. So suppose if you get this information over here, now this total information, it would be, in the case of SEM, it would be 10 to 100 nanometer. However, in the TEM, it is only 1 to 10 nanometer, okay. Now you say, sir, but you said that in 10 the electron beam passes through, okay, then how it will pass through the sample? That is the reason when we are going for the TEM analysis, the sample size of your sample should be in the order of this one. However, we can also go for the analysis up to 100 nm, but the quality would not be as good as this one. So in 10, you have to make very thin or very small samples, so that the electron beams, they can efficiently pass through the system, because their depth of resolution is very low. Then lateral resolution, it is 1 to 10 nanometer, and in this case it is 0.1 to 1 nanometer. And lastly, magnification, if you see in SEM, it is 10 to 5 lakhs, yeah, and it is 10 to 10 lakhs magnification you can achieve, 2000 to okay. So if you see, it is much higher than the scanning electron microscope. So with this, I complete the chapter.